right, we're on. Who's here? Good afternoon. I decided to leave my video on today. Someone should be here. No one? All right. I'm going to begin. I want to start with the bin problem. I'm just going to do one, and then I'm going to move into the sampling distribution of a statistic. So, let's see. So here's the problem. Now this is a problem that was done in the notes. It was completed in the probability unit, but this time we're going to do it a different way. We're going to approach this problem using the binomial formula. Right? And in fact, this is on page 12 of your notes, and I think I did do a video on this among the videos that I shared with you in Moodle. So let's just look at this together. The gene for albinism in humans is recessive. That is, carriers of this gene have probability 1/2 of passing it to a child. And the child is albino only if both parents pass the albinism gene. Parents pass their genes independently of each other. Okay, so you could solve this just using probability rules. But the idea here is to use an example for which we know the answer to derive the solution or the final answer using a different approach. And the approach we're going to use is that of the binomial formula. This is binomial. The first question, if both parents carry the albinism gene, what is the probability that their first child is albino? So we need to set this up. We need to identify, hi Divya, we need to identify the parameters, the elements of the problem. They are, actually I'm going to go to the answer here. This is just on the next page. So if we set this up, we have to identify the x, the n, the p, and the special k. So, realize that let me okay, so that's not showing. So what's the x? Let me make this a little bigger. So in this problem, we want to repeatedly look at parents. And how many times do we want to look to determine if their child is going to be born albino? We have to look at both parents. Okay, that's all we have to look at. So we look at one parent and a second parent, and we assume that the probability of one parent carrying the gene is not affected whether or not the other parent carries the gene. Okay, so they're independent. So in that case, x, we define n equals 2, because we're going to look at one parent and then the second parent. So it could be that neither of the parents have the gene, one of the parents have the gene, or both have the gene. You see how we do this? And then what's the probability of passing the gene? The probability that a parent passes the gene is known to be 50%. Okay, so we're going to check if they pass the gene. The chance of passing each time is 50%. And we're interested in the probability that the first child is albino. So the child will be albino provided both of them pass the gene. Hola, Natalia. Both of them pass the gene. So that'll happen when this happens, okay, when x is 2. So that's what we have to solve. So we set up the binomial. Set up the binomial. Right, the probability. The probability that x equals 2 is equal to the number of ways of seeing two things out of 2 times the probability of passing the gene, probability of success, to the number of successes, and I want 2 times the probability of failure to the number of failures. So if there's 2 successes and there's 2 tries, that means that there must be no failures, right? So we simplify, and we can enter this into our calculator. This will be 1, as discussed yesterday. The number of ways of seeing 2 things out of 2 is 1. 2 successes out of 2 is 1 way. And then anything to the power of 0 is also 1. So all we have to do is figure that out. Okay, 0.5 squared, which is 0.25. Very good. Any questions? No questions? Okay, so there's no questions. I'll wait to hear those of today that I can't seem to figure out how to prevent. Let me save this. And then let's move into SDS. What happened there? I'm not sure why that turned on. Why did that turn on? Any questions about the problems I already did? Hopefully you watched the videos. So what we're going to talk about next is SDS. SDS stands for the sampling distribution of a statistic. Okay, and here's the idea of the sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So what I'm doing is I'm going to look at the sample. I'm going to calculate a statistic from it, the sample of size n, and then I'm going to record that in my Excel spreadsheet. Now, what could be the possible statistics I'm interested in? Well, it's the same notion for deriving a sampling distribution, but in particular in this course, we're going to do this for x. So x, that symbol is going to represent the count of the number of successes, for instance, in sample size small n. P hat is going to be the symbol I use for the sample proportion. What is the sample proportion? The sample proportion so what is the relationship? What is the sample proportion? So sample proportion, P hat, is not the number of successes out of n trials, it's the proportion of successes out of n trials. In other words, I'm going to take the number of successes, which I'll use the variable x to represent, and I'll divide by the number of trials. That's P hat. Right? And you'll see that again and again. And finally, the other statistic I'm going to be interested in is x bar. They're large because they're representing the variable. Okay? The individual values it takes on will be denoted by a small x. Or, yeah. So this is the sample mean. Sample mean. The sample mean in one sample, for one sample, it would give us one value, but let's say we resampled, so we took another sample from the population and calculated another mean. Now, the observations in the sample might be different, they might be similar, but it'll result in a new sample mean. So imagine considering all possible samples and calculating the statistic from each one, recording in your Excel spreadsheet. Okay? And then what? So now I have an Excel spreadsheet with all the possible means in it, if that's what I was interested in. Or let's say I was taking a sample and I was calculating the number of successes. Okay? Each time I grab a sample, I calculate the number of successes and I put it in my Excel spreadsheet. I do it with one sample, then I try a sample again. It's a different sample. I count the number of successes I'm looking for, and I put it on my spreadsheet. And I repeat that. I put it on my spreadsheet, and I repeat. Take another sample, different sample, count the number of successes, put it on my spreadsheet. So now I have a spreadsheet with a whole column of statistics in it. Now the issue is, the one that I got is one from a distribution of all possible statistics I could have had. The question is, what does that statistic, what does the distribution look like for that statistic? Okay? What should the distribution look like? That's what we're going to enter into when we talk about SDS, the sampling distribution. So what should it look like? You guys can ask questions. You want me to stop? Did you understand? Did you follow? So that I could be doing that. I could replicate that for the sample count, the sample proportion, the sample average, sample mean. I can do it for other statistics as well, but these are the ones we focus on in this course, okay? So, we're going to derive, I'm going to explain to you how we understand what that distribution is going to look like. So this is the theory, the foundational support for what, how we're going to use this information later. Okay? So we're going to begin with the count variable. Where x we refer to as the count variable. Remember the number of successes, when we look at n observations, or we attempt to observe it n times. So x is referred to as the count variable. We will begin with describing the sampling distribution of x. So I have a lot of mathematics here that might be menacing. Let's see if I can just skip over, and I'll go back to that later because I think I might lose you. We'll jump into this right now. So we're talking about x. And I do have a video. You can watch another video on this on my channel. So whenever I say this, you can watch in StatsLongobardi. You can watch a video on this page as well. So I want to know about the distribution of x. What is the distribution of x? What is it distributed as? Well, usually, let's leave the shape aside for a minute, right? Let's talk about the mean and the standard deviation, and then we'll go to the shape. Usually we do it the other way around, but in this case. So what should be the mean? What should be the mean of the count variable? Well, it turns out that the mean, the distribution, the mean of the distribution of all possible outcomes will be n times p. Now, how did I get that? Okay, remembering that for x, where x is binomial, we already know the distribution, so what am I talking about, right? So we already know x is binomially distributed, but what I'm interested in knowing is, could this be distributed as a normal distribution? Or more generally, could it be distributed, could we see it as a continuous distribution? These are kind of one and the same question. So for instance, what am I talking about? Okay, so let's do the example and then I'll go up. So this is my example. Let's say x is distributed binomial with an n of 5 and a p of 0.4. And you could derive each of the values in the probability distribution of that. Oh, this got standard here. So for 1, this would be for 0. This would be for x equals 1. This is for x equals 2, all the way till x equals 5. And the values here, I'll just substitute it here, 0.0102. Right? Now, that's the distribution. If I was to depict it graphically, it would look like that. All right, remember that for a discrete distribution, which a binomial is, these are just spikes. These are just spikes. There's no area, there's no density in between. And the spikes should total in height, if you added them up, they should total 1. I could talk about smoothing out the curve, but still, that's the density. There's no area in between, but you can still talk about the shape in that sense. The shape here is symmetric. It's not perfectly symmetric. It's roughly symmetric. Should we expect it to be symmetric? As we talked about last time, we expect the distribution of the binomial to be symmetric. when P is 50%. P is not in this case, so it's fine. It's not symmetric. Okay, so what is its mean? It looks like the balancing point. Remember what the mean is. The mean is the balancing point of a distribution. So this distribution, does it balance here? Well, possibly. Let's see if we can calculate it. According to the formula I gave you above, all I have to do is multiply n and p. So 5 times 0.4 is actually 2. So yes, that is the balancing point. That's going to be the mean of the distribution. And then I can calculate standard deviation using this other formula. So where do these formulas come from? So let's go back up. So if x is the count variable, it's binomial. Think about the example the example that I provide to help you understand where this formula comes from. Imagine if you know of a basketball player that makes 80% of their free throws, 80% of the free throws. But then you see that they try to make 10 free throws, one after another. Assuming that every free throw has an 80% chance of being successful. I hope you know this terminology. That 80% of the free throws are successful that sinks the basket. So %, 10 times. So how would I figure out what to expect? Well, each time it's going to be 80%, so I just multiply by 10, and that indicates that 8 should be the expected value, okay? So now, so what does that mean? 8 is the expected value. It means that if that basketball player does it today, the chance, if we were to bet on how many free throws would be successful, how many of the shots we get in, then we should bet 8. I might not get 8, maybe he'll get 6. Maybe he'll get 6, maybe he'll get 10, maybe he'll get 4. But if you keep on repeatedly having this, conducting this daily experiment, and you do it for, I don't know, a whole year, then after the entire year, on average, out of all of those tries, so the first day it was 6, the next day it was 8, the next day it was 10, the next day it was 4, the next day, etc. And then you average all of those. So you imagine putting those in your Excel spreadsheet and taking the average. The average of all of those will be 8. So this is the concept, okay? This is the idea of the sampling distribution of the sample mean. So that's the expected value on any given try in any given sample, and that's how we calculate it. So you should have an intuition for that, because it makes sense. I just take those two numbers and multiply them, and in fact that is the case. Now the page before, where I had all those formulas, I actually derive it mathematically where that comes from. I actually derive n times p is equal to 0. What about this formula? Similarly, this formula can be derived. This is the standard deviation of that distribution. Okay? So the standard deviation, now the mean in the drawing that I made is pretty clear. That's the balancing point there. But what's the standard deviation? Remembering what the standard deviation is, we usually use it for symmetric distribution to help us imagine or illustrate how spread out the values are, and the standard deviation within 3 standard deviations should cover within 3 standard deviations of the mean, you should be able to capture the range, the full range of data. And so while we want to calculate the standard deviation for this, even though it's not symmetric, but we can calculate it nonetheless. Okay. So we do that with this formula here. Now where does that come from? Same idea. It comes from the derivation on the page before. How do I calculate it? Well, just punch in. Standard deviation is n times p times 1 minus p with a square root around it. So the standard deviation is 1.095. So this distribution is not symmetric, but we can calculate its mean and standard deviation. Could come in handy. It's a nice way to represent the distribution. But we're more interested in binomial distributions that are symmetric. And it turns out, without deriving it, you're just going to trust me, that the binomial distributions that are symmetric, as I mentioned to you, are when p equals 0.5, symmetric. The binomial distribution is symmetric if p equals 0.5, but it's also symmetric if it satisfies these two criteria. First, if n times p is greater than or equal to 10, so its mean is bigger than 10, and n times 1 minus p is bigger than or equal to 10. If those are both satisfied, then we can say that x is approximately, that's what that symbol means, you remember the symbol, x is approximately normal, and remember the first element here is always the mean, and I'm going to put a little x on it just because I want to distinguish it from the other two that I'm going to introduce you to. I'm going to do this, this sort of thing where I talk about the sampling distribution of a statistic again, so I want to distinguish this one from the other. So this one is mean of x, and then this symbol will be, well, that's the standard deviation, so I use a symbol for standard deviation of x, the count variable. Okay? So, how will we use this? Well, let's first go back a step, and I can derive this for you. And I'll try not to let your eyes glaze over. The derivation of this, you'll see, is it's based on the rules for means and variances, in fact. And so this is where I'm heading, just to show you where I'm heading. I want to show you that the mean of x, where x is binomial, x is the result of summing each of these. These are Bernoulli trials. So in other words, I'm going to look, remember what's a binomial, I'm going to attempt to look for my success n times. And the outcome of doing that is actually a variable. It's going to be S1 will denote the outcome on the first try. And S2 will denote the outcome on the second try, etc., all the way to Sn, which will denote the outcome on the nth try. Right? So, is my new variable created from n other variables that are all identical. So I'm going to use the expected operator, right, the E operator, which we learned about for rules of mean and variances. The mean of a sum of variables is the sum of the means. Right? So all I need is to know the mean of each trial, and then I can sum those up. And that's how I get the answer. So where does this come from? That's what's above. That's what you're going to see above. Okay, so we call it a Bernoulli trial. The Bernoulli trial the Bernoulli random variable indicates success or failure. Success or yes is 1, and failure is no or 0. So here are the possible outcomes. Success is 1 with a probability p, and failure is 0 with a probability 1 minus p. And I can calculate from there the mean. So how do I do that? The weighted mean, right? Probability times outcome plus probability times outcome. And that's how I get this p. Isn't that cool? See, so this times this is 0, and this times this is just p. So that is the mean of the Bernoulli trial. Each time I look and observe, attempting to find my success. What about the variance? Variance is calculated as the weighted deviation from the mean, right? The average of the, so it's the weighted standard deviation, or the weighted variance. So that is going to be the deviation squared from the mean, weighted by the probability weight. This is, again, go back and see, this is just the variance for an ex-ante problem, where you have probabilities of outcomes, and I have a whole distribution given here. So how do we do this? I go through each option. So this is option 0. This is a possible outcome. So 0 minus the mean. The mean is from here, p. You square that, and then you multiply by the probability 1 minus p, and then you do the same for this outcome. 1 minus the mean. The mean is p, so I square that and multiply it by its probability p. So this is just algebra. You know, don't let it upset you. Just a bunch of algebra that's actually pretty neat. And then when you work it out, you find out that this is the variance of the Bernoulli trial. So these two results, the mean and the standard deviation of the Bernoulli trial, are used here. So for each one, and I'm going to try n times, I just sum their means, and I get np. And for the variance, I just, because they're independent, remember the trials are independent, you see the importance of that. It's a very simple variance formula, because if trials are independent or variables are independent, then the variance of the sum of these variables is just the sum of the variances. So I just add up all these, and there's just n of them. So I'm never going to test you on this. I just think it's kind of a neat exercise in applying means and variances, and you see the utility in learning about means and variances, because the distributions we're going to use are derived from those rules. So those are the results that we're going to be using from here on out. These are the results of the mean and variance for a binomially distributed x. All right, so you don't have to memorize them, but it's handy to keep the formula sheet that's at the end of this unit at your side, so you can refer to it easily. Let me show you that formula sheet. So that formula sheet is here, and what we've just discussed is number 1. So from today's and yesterday's class or this week's classes, we've already captured the elements, the information in one. So I've introduced this idea that x is binomial with parameters np. So x has a mean of np and a standard deviation np 1 minus p square root, because we want the standard deviation, not the variance. We have to take the square root. And this is the binomial formula that we discussed yesterday. And now I'm going to talk about this part. So what does this say? X is binomially distributed, but it's also approximately normally distributed, provided that n times p is larger than or equal to 10, and n times 1 minus p is larger than or equal to 10. And the population size is large. Those are the conditions. So going back to where I left off, this is an example here. Here we have the threshold where this all begins with p of 0.5 and n of 20. That's the only scenario where a distribution will be, well, anyway, it's a launching point for where a distribution will be symmetric if p is not 0.5. But again, if p is 0.5, the distribution will always be symmetric. But other than that, if p is not 0.5, you can conduct this check. So in this case it is, so let's just work with what we have. So this looks symmetric, right? What did I do though? Something's different here. I've done something. And so I put the possible outcomes here, and I put the letter K because we like to use K instead of little x. We use little K. And then here the heights are the probabilities, and that sum of the probabilities should be 1. So in other words, the sum of the heights should be 1. But what I've done is I put some density around each spike. And what I'm doing there is I'm creating, or I'm connecting the discrete to the continuous distribution. And it turns out I could smooth that over, and under there would be 100%, I can think. And this is going to be an approximation in the approach that we're going to take. But to make it exact, I'm going to talk about how to make it more precise. All right. So what do I do with this? Well, this is really handy, that I can use the normal distribution rather than a binomial. Makes it possible that I can answer questions for distributions that are rather large, where the sample size underlying the distribution is really large. Okay, so remember, this is a binomial distribution. It depends on the sample size, the number of trials. So I'll show you what I mean. So let's look at a couple of examples. Let's say that x is binomial with a mean of 100, sorry, not a mean, an n of 100 and a p of 1/3. Suppose I want to find the probability that x is greater than 23. Well, as far as we're concerned, what we've done so far is we've learned about listing all the possible outcomes, right? Listing all the possible outcomes, and then identifying which ones we have to calculate using our formula. In this case, we would have to calculate, to answer this question, all the probabilities, 24, x equals 25, x equals 26, up all the way to x equals 100 and add them together. We could do this with Excel, we could do it with a binomial distribution table, but we could also do it this way. In the absence of those, or if it didn't matter that we were so precise, we could do it this way. And this way is first, we have to check that we can actually assume that the distribution is symmetric. So we take n times p, and we check, is it bigger than 10? Yes, it is. Then n times 1 minus p, is that bigger than 10? Yes, it is. So that means that we can make the approximation. So x is distributed approximately normally with a mean of np and a standard deviation n times p times 1 minus p square root. Next step, let's calculate those parameters for the normal. The calculation is here. So you should punch this in to verify that you know what I'm doing and that you know how to use your calculator. N times p is 33, and n times p times 1 minus p. So multiply those together, say equals, and then square root to get this number. Okay? And then with those values, what we can do next is answer the question. How do we answer the question? Go back to the normal distribution. All they have to do is, if I know it's normally distributed, I can standardize it. The probability of x being greater than 23 is a matter of standardizing. When I do that, using the mean and standard deviation I've computed, based on the theory which we derived, then we're looking for the probability that z, the standard normal distribution, is greater than negative 2.19. So drawing a quick picture, right? Negative 2.19 is here, and I want to go this way. And this is what you want to get. That's not in the table, so we have to go the other way to be in the table. So we take 1 minus that to get the answer. Okay. So the answer is 98.57. So the chance that so what is this, going back to the problem? A binomial distribution. So there's 100 trials, and the chance of getting or seeing what we're looking for is 1/3. We're going to try 100 times. Out of those 100 attempts, the chance of seeing our success more than 23 times is very high. So it could be any of 24, 25, 26, more than 23. The chance is very high. It's 98.57% chance. Okay? So, what about, this should make you think about the problem that we posed about ESP. So finally, we have a technique that will facilitate answering this question. If you have 100 cards guessed by a person to assess whether they have ESP, and their chance of getting it correct on any try is 25%. What is the chance, by simply guessing, that the person will have ESP? I just noticed that my microphone was off. I'm using that computer microphone. I hope it's been okay. Let's see. Plug this in. I wonder if that's better. Can you hear me? Can you hear me? Everybody hears me? Hello, hello, hello. Testing, testing. I always forget something, it seems. Audio. Yeah, I think the microphone is picking it up. Okay. Alright, so this is the problem for ESP. This is the problem for ESP. So 100 cards are shown to an individual to determine if they have ESP. The chance of, by guessing, actually getting the card right, because there were 4 different images and there's no reason to think guessing any particular image is going to be correct. There's 4, so they each have 25% chance out of 20 or 1/4. So 4 alternatives, 1/4 each in the sample space. That makes 1 or 100%. So I want to find this. I want to find out what's the probability that he guesses 50 or more correctly. Again, this is daunting if I actually have to compute for all of those, that's going to take a while. So instead, I'm going to adopt the normal approximation to the binomial. First, I'm going to check if I can do it. I need to check that n times p is greater than 10, and it is. And n times 1 minus p, which is 75, is also greater than 10. So the normal approximation to the binomial is fine. So I substitute in the mean and the standard deviation, which I actually derive in the second part. So n times p is 25, and n times p times 1 minus p equals square root is 4.33. And using that mean and standard deviation, I can go back to the original question and standardize to solve. And what do I get is this. What is the probability that the standard normal is greater than or equal to 5.77? Well, that's right off the chart, right? It's right off the chart. And in our case, in this case, say I'm here, 5.77, and I need to go this way. The chance of being almost 6 standard deviations above the mean, if this is a normal distribution that we've assumed, then the chance of being there is so small, we're going to call it 0. So the chance that somebody just guessing, this is in conclusion, the chance that someone just guessing would be found to have ESP is so small, we're going to just call it 0. Okay, 0 chance. Okay, so that's what you do with the count variable, and really I don't have too many problems like that, but you need to be prepared if I ask you questions about the binomial variable x or the count variable x, or I'm talking about the number of successes in independent trials. Those are all the same. Those are all the same variable. And so you would use the same approach. What about if, and this is the more common variable, usually, you know, when we talk about how many successes out of n tries, like how many people out of a sample or a poll approve of the Democrats, or what percentage of people tested have tested positive for the coronavirus. You know, these are percentages, right? They're not counts. We don't usually say, well, we do say sometimes, you know, the number of people, but often people speak in proportions. So for that reason, we derive the sample proportion measure. And the sample proportion is very straightforward. It's the theories all fall or come from the one that we just learned, but I need to show you how we can make this step in the direction of the proportion. So let's lay this out. The mean and standard deviation of the sampling distribution of p hat and the normal approximation. Remember, p hat is the statistic, right? It's what I calculate from the sample. And it comes from calculating the number of successes in n independent trials and dividing by the total number of trials. So for instance, if there are 50 successes out of 100, then that would be 50%. So though the x was 50, the p hat would be, well, in this case 52. It would be 50% or 0.5. All right? So this is x, but this is p hat. All right, now let's put it all in perspective for you. I actually started, I didn't write it here, but okay, x, I don't have a symbol for x. Let's say the population parameter was the total or the actual, let's use the word actual, the actual number of successes. So if we had the whole population and we knew the actual number of successes, whatever we were interested in, we knew the actual number, this would be estimated by the random variable or the sample statistic x, okay, which I treat like as a random variable for which I derive a distribution. So this is the one I just talked about. P is the actual population proportion, and I'm going to estimate it by p hat, the sample proportion. Similarly, sigma is the population standard deviation, and it's estimated by S, the sample standard deviation. And the mean is the population mean. It's estimated by x bar, the sample mean. Okay, you've seen this chart many times before. I just wanted to throw this one under because we don't, I'll put it here.
in its position. Even though I don't talk about it a lot, it is the foundation for the proportion which people use a lot. Okay, so, oh, I derive all of this online. I know that because I put a notation here. So you can look at the derivation of that. And some exercises here. Do you have any questions? Let's see what I can do that's going to be useful here. The most important thing to say is, okay, we learned. Actually, let's do it this way because I only have 5 minutes. I'm going to speak about it here. This is a summary of where I'm going with this. So we already talked about number 1. For a binomial variable x with parameters n and p, its mean will be np, its standard deviation np1 minus p square root. Each outcome is calculated using this formula. It's a discrete variable. And in fact, the distribution will be symmetric and approximately normal provided n times p is larger than or equal to 10 and n times 1 minus p are larger than or equal to 10. So it's not just symmetric, okay? It's actually going to be viewed as approximately normally distributed. And I do derive that in the notes. And this is what I'm talking about next. If x is binomially distributed with parameter n and p, then we also have the possibility of computing the sample proportion, and it is the sample proportion we calculate from any individual sample comes from a distribution of sample proportions. That distribution has a mean and a standard deviation. Now the mean of this will be p. The mean of p hat is p. Isn't that weird? The mean of p hat is p. The mean of p hat so if I write this symbol, mean of p hat is p. Does that bother you? But that's in fact what it is. The mean of p hat is p. Now where does that come from? And the standard deviation of p hat is this here. Okay, so that looks familiar. Should look familiar. If this is the mean of p hat, let's remember what is the mean of x. The mean of x, remember p hat is just x over n. Do that again. I didn't do that good. So p hat is x over n. So the mean of x, we said, would be np, remember? P hat is x over n. So whatever I do to the values of x, in this case dividing by the n, I should also do the mean, correct? So shouldn't the mean just be divided by n, just like x is divided by n? Of course it is. That's where this comes from. All right? So that is because of the properties of means and variances. The variance also, or the standard deviation, will have the same result. And that's what I'm going to discuss, I guess, tomorrow. But you can go ahead and look at the video that I already posted on this to see that. But that was just a preview introduction to what I'm talking about. And that result, very important result. There's a lot of notes here. That's why I didn't want to abandon you. One more slide. So here, you see? P hat is x over n. So the mean of p hat is p, which comes from taking the mean of x, which was np, and basically dividing it by n to get p. So this divided by n gives me that, just like x was divided by n. Similarly, sigma x, which is the square root of np1 minus p square root, that's an n there. This sigma of p hat is just the sigma of x divided by n. If I divide this by n, I will get that, and you can see that in the calculations below. So verify that. Have a look at all of that for next time, for tomorrow. Tomorrow at 5, I'll have a discussion, and then at 6 I will put a quiz. The quiz will be on the binomial material up until what I did today, so for Monday and Tuesday. So it's just going to be a binomial problem. And then next week will be the SDS. So let's make some headway with SDS. I'm going to provide a lecture on SDS tomorrow and then on Friday as well. And that should be enough to prepare you for the next week quiz on SDS, right? So keep up and make sure you send your questions in advance. You have lots of exercises to attempt. Keep organized and keep on keeping on. Bye.